Hello everyone, this lesson is about power and work in circuits. So the learning intentions: understand power and work in electrical circuits. By the end of the lesson you should be able to define power in an electrical circuit, rearrange and use the power and work equations in electrical circuits. There's a starter question here. Write the equation for resistance at V2, looking at the graph shown. Describe how the resistance changes from V1 to V2. Pause the video and have a go at that. The equation for resistance is V divided by I. So in this situation we've got the resistance at V2 is going to be equal to V2 divided by I2. Describe how the resistance changes from V1 to V2. So we know the gradient of an IV graph is equal to 1 over R, or the reciprocal of resistance. And we can see 1 over R is increasing from V1 to V2. So that means R, the resistance, must be decreasing. Key definition: power, the rate at which work is done, and the rate at which energy is transferred. P equals change in work or work done divided by time taken, which equals energy transferred divided by time. Remember, if we're talking about the rate of something, we will be dividing by the time taken. What are the units of power? So what is the unit of power is the question that answers itself. Unit of energy, joules. Unit of time, seconds. Then 1 watt equals 1 joule per second of energy transfer. We can derive the power equations from equations already covered. We know the equation for potential difference equals work divided by charge, and so V equals W over Q, and the equation for current equals charge divided by time, so I equals Q over T. There's 3 steps here to derive the equations for power that we need. Step 1, divide W by VQ. W equals VQ by T and substitute Q over T. Pause the video to see if you can do that. So we get power equals VQ over T. I've just written VQ instead of W. VQ over T is equal to VI because Q over T equals I. So we have our first equation for power. Highlighted in yellow here, we can see that power equals V times I. Potential difference times current. On to step 2. Substitute V equals IR into that equation. And then, second step, substitute I equals V over R. And you should find you arrive at 2 further equations for power. So shown in red here, P equals VI, which equals IR times I, which equals I squared R. So you can see we've substituted in, instead of V, we've written IR. We multiply that by I, that gives us I squared R. So that's our second equation for power. Here's a third one, so P equals VI, which is equal to V, multiplied by V over R, which equals V squared over R. So we've substituted in for I, instead of I, we've written V over R, and so the equation then becomes V squared over R. So that's our third equation for power. And so we have power equals V times I, which equals I squared over R, which equals V squared over R. So 3 different equations depending on what we're given and what we need to find. We can also write work done equals power times time, which equals IVT, which is an equation we'll often need to use in electrical circuits where we are measuring potential difference and current and time. These derivations are not needed for the exam. However, the ability to rearrange equations is essential, so it's good practice to be able to do them. This is a question now for you to try using the power equations. Worked example. The power dissipated in a lamp is 1.5 watts when its resistance is 24 ohms. What is the current through the lamp? Pause the video, write down your working, and your answer should have the correct units. So just put out the values you've got. Power equals 1.5 watts, resistance is 24 ohms, and so we're going to use power equals I squared R. Rearrange that to find current. So I equals the square root of P over R, which equals the square root of brackets 1.5 divided by 24. And you should get an answer of 0.25 amps. Here's a second question for you to try. A simple radio has been left running for half an hour. Here is a circuit diagram for the system. The radio is powered by two standard 9-volt batteries. Assume that there is no internal resistance. Both the speaker and receiver can be treated as standard resistors with a resistance of 2 ohms and 3 ohms respectively. Question A, what is the overall power rating for the radio? And B, how much total energy has been used by the radio for the time it has been switched on? First thing here will be to pull out the values and put them onto the circuit diagram. It just makes things clearer. So we've got two standard 9-volt batteries, so it's going to give us a total potential difference of 18 volts. That's our terminal potential difference. We can label the resistors of the speaker and the receiver. So for part A, there are two methods. You can either do the power equals I times V method, or you can find the total resistance of the circuit and then do V squared over R. Either way, you should get to an answer of 243 watts. So the IV method, we know that the total circuit current, labelled here I, is equal to I1 plus I2. That's the sum of the currents through the branches. And we know that we can find the current through each branch from the potential difference across it divided by the resistance. So I1 equals 18 volts divided by 2 ohms, which is 9 amps. I2 equals 18 volts divided by 4 ohms, which equals 4.5 amps. And we then add those two currents together. 9 plus 4.5 equals 13.5 amps. And then we do P equals I times V. So it's 13.5 amps times 18 volts, which is 243 watts. The alternative method, shown on the left here, is to find the total circuit resistance and then use V squared over R. So using the 1 over R total equals 1 over R1 plus 1 over R2 method, we get 1 over R equals 1 over 2 plus 1 over 4. So remember, it's a 1 ohm and a 3 ohm resistor in series, so that becomes a 4 ohm resistor. So the half plus a quarter, which equals 3 quarters, and then R is the inverse of that, so 4 over 3, which equals 1.33 ohms, and then V squared over R becomes 18 squared divided by 1.33 equals 244 watts. I think the difference there is just in the chopping off the sig figs a bit to 1.33, it's 1.3 recurring, and that might get you a little bit closer to 243. And then for part B, energy equals power times time. So it's 243 multiplied by 30 minutes multiplied by 60 seconds. This is 4.4 times 10 to the power of 5 joules. Check your working, make any corrections that you need to. Well done if you got those right. There's 3 questions here I'd now like you to pause the video and work on. Remember to show your working. So first one, I equals P over V, 10 over 5 is 2 amps. Part B, R equals V over I, so it's 5 volts divided by 2 amps equals 2.5 ohms. Question 2, total energy input, energy equals power times time, 2.2 times 10 to the 3, remember it's kilowatts, So we times 10 to the 3 to get it into watts, times 3 for 3 hours, times 60 minutes, times 60 seconds. That gives us 2.376 or 2.4 times 10 to the power of 7 joules, two significant figures. And then for part B, so this TV has an efficiency of 40%. That means that 60% is wasted. So 60% of the value just calculated, 0.6 times 2.4 times 10 to the power of 7 equals 1.44 times 10 to the 7 joules. And then for question 3, using formulae, show that a feasible unit for charge is watt seconds per volt. So watt is the unit of power, seconds is the unit of time, volts is the unit of potential difference. So we can write that as PT over V. So the question is Q equal to PT over V? So a quick rearrangement there shows that QV equals work, which also equals PT. So this is a feasible unit. We've shown that. So we're now on to trying some exam style questions on this topic. Pause the video and have a go at this first part, 15A and 15B. I'd like you to self-mark 15A and 15B, 2 marks for each section. Part A, the marks are for use of power equals V squared over R, or P equals IV and V equals IR. And R equals 48.4 ohms, except 48 or 50 ohms. Examples of calculations shown. 15B, 1 mark for use of energy equals power times time, or energy equals IVT, or energy equals V squared T over R, with 3 or 3 times 60 as the time. Energy equals 180,000 joules for the second mark, that's the correct answer. If you have 3,000 joules, then that scores just 1 mark for this section. You can carry forward values of R and or I from part A. This is a continuation of the question. C part 1. Pause the video and have a go at this. And here's the marks, the 3 marks available. So if you've attempted to calculate the power, 1 mark. Power equals 250 watts, 1 mark. Time to boil, 12 minutes or 720 seconds, noted down, 1 mark. Or there's 2 other alternatives as shown. One is to calculate a new current, 2.27 amps. Use of energy equals IVT with your value of current, and use of time is 720 seconds or 12 minutes. Or you can use power is proportional to potential difference squared, which is proportional to a quarter. So T is proportional to 1 over P, which is proportional to 4 time 12 minutes. For any method, an answer of 6 minutes scores 1 mark. And now the final part of this question, C part 2. Pause the video and have a go at this. So C part 2 answers, use of the equation, one of the equations, V equals IR, or power equals V squared over R, or P equals V times I, leading to increased current or power. So it could cause damage, it could cause the fuse to melt, circuit breaker to trip, element to burn out, wire to melt. Do not credit short circuit and explosions. Do not award the second mark if the reference to overheating or fuses is related to resistance increasing. So total for this question is 9 marks. So check the success criteria for this lesson. Can you define power in an electrical circuit, and can you rearrange and use the power and work equations in electrical circuits? And if you've been getting most of the questions correct, then the answer is yes. So well done for doing that. If you're not so sure about anything, you can always go back and have another look at the video. All right then, everyone, thank you very much. Bye for now.